In this lecture, we will analyze a specific particular molecular device for a particular application, which is called molecular quantum dot cellular automata. The lecture is organized in these 4 parts. We will start with a brief motivation, and then we will analyze QCA theory to step forward to the specific molecular implementation with the aim of analyzing some particular molecules. So we all know that in the last years the amazing scaling down of transistors has given a transistor density that allowed to pack a lot of functions in the same circuit and to achieve very high frequencies. But this has also been associated to a very huge power density. So what should we expect for the next years? The International Technology Roadmap of Semiconductor confirms a dramatic increase in power dissipation. And if we think briefly at the history of the computation, we can see that power dissipation has been a pick lock in all the fundamental technology changes. If we think the first computers were just mechanical, and then we had a great variation, a great improvement with vacuum tubes. And there the power consumption was the pick lock to move from one technology to the other. The same kind of step we assisted to the same kind of steps when from vacuum tubes we stepped to transistors. And after that to integrated circuits based on transistors. So what do we expect from the next step? If we think that the future leads to the concept of molecular transistors, we should expect a charge transfer of 1 electron or few electrons, but this will for sure give us high device densities, frequency to which we cannot even think about now, but the basic point is that this molecular transistor will still be based on conduction, on transfer of electrons from one node to another node of the transistor. So what about power density in this case? ITRS prediction, for example, says that in a few years we could expect to use 9 nanometer gate length transistors, which could assure 1,000 million transistor per square centimeters for a frequency of around 30 gigahertz. So if this is more or less a reality to be expected, what if we step to a molecular transistor? Here we have some example of prediction. So if we increase again the density that could be expected with a molecular transistor with a frequency of this size, 10 to the power of 11, the number of watts per square centimeters can be just pronounced with some difficulty. So the idea, the question is, are we going to compute, or are we going to to test a new type of cooking style here? So the idea behind quantum dot cellular automata is exactly that of change paradigm in order to reduce power dissipation. So the idea is to use molecules no more as current switches, but to use them as structured charge containers. So the idea is to not having any more flow of electrons, but just transfer of charge. So let's go to analyze the QCA theory. QCA have been introduced by Land a few years ago. And the idea is to have basic cells that can encode binary data, 0 and 1. Which 0, which 1, depends on the type of encoding we decide to have. But basically the idea is to have these cells organized in 4 dots, at least in the basic organization of QCA, 4 dots, each able to include 1 electron. So if we think that in one cell we can just entrap 2 electrons, so for electrostatic repulsion, then only the diagonal are occupied by the electrons. And so we can have all this case or this case. Using this idea, it is possible to place one near the other basic cells and build logic functions. For example, the one we have here is an inverter, organized using a few cells. And in this case, we have, so let's say that this is a 1, and you see that here we have a 0. What happens if we change the input? If we change the input from a 1 to a 0, then, due to electrostatic interaction, we will have the passage of information without a transfer of electrons from one cell to the other. Just electrostatic repulsions forced the second cell to move to a new state. And let's go on in a domino-like style. So we have the propagation of the information down to the last cell. This very principle can be used to build also other functions. For example, here we have a majority voter, which is basically the base cell used to build all the basic logic functions. This majority voter is based on 3 inputs, and the output will assume the majority of the value assumed by the majority of the inputs. For example, in this case, we have 2 inputs in which the electrons occupy this diagonal, and this is in the opposite case, and so the output is forced exactly as input 1 and 2. Typically, this is the symbol used, and it is easy to analyze, to see that if we force one of the input to 0 or to 1, we can stick the logic function of the majority voter to a AND or to an OR gate. Clearly, having these gates and having the inverter, basically, we can build whatever we want from the logic point of view. Still, we also need the propagation without elaboration of the information, but just a propagation from one point to the other, so we need a wire. In this technology, a wire is not just an interconnections like in CMOS, but still is a cell which holds the information and copy it to the nearby cells. And using the same principle, we also need to move information in 2 directions of the circuit, horizontal or vertical. And so in this case, a specific block, which is called the crosswire, is being used. Because clearly, at least at this stage of the evolution of this technology, we don't have the possibility to use 3-dimensional interconnects. Using all these basic cells, then it is possible to build even more complex structures. Like in this case, we have a full adder based on several wires, majority voters and inverters. And here in this part, we have the very same structure, but with explicit QCA cells. Now, using this as a base, it is also possible to go up in the design level and to go toward the architecture level. There is a big research community working on this, and the problem related to this is that there is not a real connection to the physical behavior. The typical work in QCA literature is, okay, let's assume that some QCA cell exists and that works properly, and then it is possible to build another an arithmetic unit, even a processor. So clearly, this is not so realistic. A realistic QCA structure and research associated to this structure should take into account real blocks and should be able to model the behavior, taking into account the effects and the real environment influence, to do measurement and to refine the models using measurements. At this point, it is possible to step to a higher level and to design and analyze the circuits. So one of the most important realistic structure to be considered is the clock system. The concept of clock here is totally different with respect to what we normally consider a clock in digital CMOS circuit. We call it a clock just because it's associated to a signal which steps up and down cyclically. So this is the reason why. But the idea behind that is different. So what's the problem? We have seen before a wire, for example, of few gates, of few cells. But the point is that even theory demonstrates that as soon as we reach realistic temperature, for example, a wire length is limited because signal can perceive a degradation from one point to the other. So we cannot think to have wires of a length, whatever length. So this is one of the problems. The other problem is that to store the information, we need a strong barrier between the two states. But this barrier also is present when we want to change state. So if we want to change the state in the domino-like way we have seen before, then for sure we have to force a big field in order to change it. So how to solve these two problems? The idea is to organize the circuit in zones. Each zone will embrace a few cells, and only a few cells per time will switch with the help of this clock. So the clock is an external signal which depends on the application, could be an electric field or a magnetic field. And the aim of this field is to lower the cell potential barrier in order to reduce the switching energy. At the same time, this zone in which the field is applied should be short enough in order to assure a correct information propagation inside the same zone. So this clock signal is alternated from 0-1 on-off, and so that the propagation is and happens in a pipeline style. To do that, the cell must be a little bit more complicated. Not only the 0 and the 1 should be encoded, but also a null structure, a null state must be assured, exactly when the clock field is on. So how it works? If we have two cells nearby, then we will have, imagine that we have a cell with a state stored, for example a 1, and we apply in the near cell the clock. So we have a null state. As soon as we release the clock, then the data is copied to the cell near, and so we have one propagation. This is much more easy with respect to the case without the clock, because in this state, to step from this state to this state, we need a smaller energy. In the same way, we can see how it works in case of a bigger circuit, like, for example, the inverter. So we start with a 1 here, for example, as an input, and all the other cells are in the null state. So as soon as we release the clock, then the information is propagated. But this time, the amount of energy necessary is slower, and also the information propagation is faster, and the total amount of energy required is smaller. And not only, also the correctness of the information propagation is assured, and a much longer wire or much longer propagation is assured. At least this is what the theory from Lent describes. A similar structure, clearly again, in the majority voter, where we have 3 stable input. We have the output in a null state. As soon as we rise the clock, then the output assumes the correct value. So this was just for one clock zone. Clock must be organized in phases. So we can think at different zones where each zone is either in a switch phase or in a hold phase, with all the intermediate step from hold to switch or vice versa. So the propagation should occur in the way we are seeing. Now, this is the theory. What about the real cases, the real implementation? There has been a real demonstration of QCA in the past based on a metal implementation. Basically, the structure that we see here is based on metal, aluminum island, over silicon dioxide. And we have 2 dots here on the left, which can be associated to the other on the right by tunneling. And these other 2 dots are coupled to single electron transistors used as electrometers, basically. And the transfer of information and the change of state from 1 to 0, from the left state to the right state, has been demonstrated in the past. Problem, this only works at few millikelvin temperature, so this is not realistic. Moreover, also, it is not so small. It's not a nano device. It's a micro device. In any case, the principle has been demonstrated. After this, semiconductor implementation has been tested, because clearly technology is solid for what concerns semiconductor. So structures based on gallium arsenide, for example, have been tested, in which several structures, several layers of silicon, germanium, or gallium arsenide are interleaved, and in which we have some dots that should be able to store charges. Now, this structure, again, has been tested, but results were not so successful because, again, it should work at cryogenic temperatures. It is highly defective, and especially if nano dimensions should be reached, it has been proved that defects overcomes the possibility of technology. So this implementation has been basically abandoned. Another successful implementation that is currently adopted nowadays is the magnetic one. So here the cell is a small magnet with a shape anisotropy in which the magnetization assumes a stable state in one direction or in the other direction. And again, in this case, we need a clock. Clearly, in this case, we have a magnetic clock field, which is able to erase the magnetization and force the magnetization in a horizontal state. And as soon as the clock is released, then the magnetization goes up or down. This type of implementation has been proved, as we see here, and is promising, at least in terms of power dissipation. Clearly, as it involves magnetism, the speed is not so amazing, but at least it can be done at room temperature, and it can be to demonstrate the idea. And then there is the molecular implementation. Let's see how the molecular implementation can work. The idea is to have molecules which have redox centers that can hold a logic state, like the one we see here on the right or in the left. And when a switching occurs, basically one electron tunnels from one point to the other, from one dot to the other, assuring a transfer of charge. And this is the only transfer that happens in this molecule. Clearly, if we have to consider also the clock, we still need cells able to assure the null state. So we need not only two redox centers, but also a third point which allows us to erase the 0 or the 1. And at that point, if we think at how molecules can interact, the idea is to put one near the other, and to and for the same principle as before, for electrostatic repulsion, the charge will be associated to will be coupled in this way, in a diagonal way. Clearly, again, we should have the clock. So, for example, in this case, we have an input molecule and a cell influenced by that input using the electrostatic interference. And in this case, the clock is not applied. As soon as we apply the clock, in this example, in this vertical direction, then the information is erased. As soon as the clock is released, then the molecule will step again to the stable state. Here we have an example in which we see a potential wire of molecules, and below the wires, let's suppose to have small metallic or what is needed wires able to deliver such clock. For example, in this case, here we in the green line here we have the clock applied, so we have a null domain here, and while in the other zone here we have a stable state because the clock is not applied, and in the middle there is a switching, because at this point, as soon as we release the clock from the right side, the information will be propagated from the left to the right. Okay, so this is the principle. The point is that the clock must be applied properly. So imagine that we have a bunch of molecules organized in zones. In this example, 3 zones. and that we are able to force an input here with a molecule or with something else. In this case, the input is such that the charge is concentrated here in this point. In the three zones here we have this part which is in the hole. Then you see that we have a correct organization of charge according to the input. In the same time, we have the other two zones in which we apply the clock that are in a null state, all the two zones. Why? Because now, in the next step, we keep the clock in the third stage, in the third phase here, but we release the clock from the second. In this way, the molecules in the second block can step from the null state to the data, using as input the molecules in the previous block, without being influenced by the molecules in the right part, which are in the null state. And so this principle is used to propagate information no more from the first to the second part, but from the second to the third. For example, here we now put the clock in this point, and the third stage can switch using the molecules in the second as input. Now, as we apply the clock here, the molecules in the first stage are in a null state. We can, in this moment, change the input, but before releasing the clock from the first block, we have to apply it in the second, so we have to superpose the clock application in different stages, and only now we can release the clock in the first, and so the molecule in the first stage can switch according to the input. So this is the way in which we need to apply the clock, and so it means that we need molecules that can be organized in zones, and also we need signals and wires that can be organized in different parts to which we force clocks dynamically in this way. Now, to complete the general description of molecular QCA, clearly we need to be able to apply this clock, to write in a data, and also to read out the value. So this is still a research at a research point. No real implementation have been done, apart from some examples that I'm going to mention later. In general, the possible clock in this case could be an electric field, clearly delivered through specific electrodes. But these electrodes clearly must be small enough and precise enough to do what we have seen before. For the writing, again, it is possible to think at electric field applied to even not merely just one molecule, but at least to a bunch of molecules. This bunch of molecules can be used as an input toward the next molecules in the next stage. And for what concerns readout, one possibility is to use a single electron transistor to sense the charge difference. To summarize, which are the pros and the cons of this molecular technology? Well, clearly we are talking about very small structure, around 2 nanometers or even a little bit more, but in any case very small, and this can assure very huge densities. It has been demonstrated in theory that they can work not at cryogenic temperature, they can work at room temperature, and so this is clearly one good point with respect to the other implementation we have mentioned before. The frequency that can be reached is bigger than 1 terahertz, around 10 terahertz at least in the optimal conditions. And the associated power dissipation is very small, as no conduction is associated to the information propagation. Clearly, the data depends on the application, on the specific implementation, the real data. But in any case, theory demonstrated that very tiny power dissipation is to be expected with respect to previous, to the other possible implementation. And the other important advantage is the fabrication potentiality. We don't need any more lithography, but because we can rely on self-assembly of layers of molecules. Now, clearly, we also have cones. The problem is that all what we have mentioned is true in theory, but still no prototype have been fabricated yet, just some attempts, as mainly because technology currently is still not adequate to manipulate single molecule or group of molecules. And associated to this, but worth pointing out, is the difficulty to sense the value. Even though if you are able to build a wire of molecules and to force an input, maybe to force a clock, how do you read? Because the charge associated to a single molecule is very small. So it's not easy to read the value. One experimental setup has been done a few years ago, but not based on a single molecule, based on a film of molecules that later we will see a little bit more into details, based on iron and ruthenium, on a film of molecules organized with ruthenium on a silicon substrate and with the iron capped with mercury, and using a particular organization of electric field applied between the substrate and the mercury, a clear charge difference has been analyzed when the voltage applied was varied between the positive and the negative. So this means that the charge transfer can be used, is true, is a real idea, and can be effectively used for computation. Still, the transfer of information between one cell and the cell nearby has to be demonstrated. So this was the previously done experimental setup. Another possible experimental setup that is now in the way of being organized, especially the Politecnico di Torino, is based on several steps. First, organize a few molecules available and put them under an electric field, and first observe their behavior using STM or AFM. Then find an experimental setup based on nanogaps that can be really done here in order to selectively apply the clock, or using again the nanogaps to not only as a clock but also as an input. And clearly the next step is to analyze, to find a way to analyze how the charge is distributed, basically to be able to read out the value. Clearly it is important to simulate this structure, and so many simulations have been done to analyze the behavior of particular molecules under the influence of electric field applied by means of nanogaps. So the idea is to use nanogaps that can be built in this university, and that exploiting the fact that these nanogaps are around 3-4 nanometers, and so small molecules can be placed here in the middle, and so an electric field can be applied between the two electrons. So this is a section view, clearly theoretical, of how the structure can be built, whether the basic substrate here is gold or silicon dioxide, and the gap is based on silicon or on gold, depends on the type of molecule available. But clearly, the molecule must be selective in terms of the fact that, that it must be connected to the substrate only where we have the gap, so that there is not a direct influence between the gap, the electrode and the molecule. The electrode is used just to force an electric field all around the molecule. And this is how it should work. This is ongoing work, and we hope very soon to demonstrate this step. Now let's analyze a few molecules and their properties that can be used for this type of application. So, which are the characteristics that we expect to have? Clearly, we must have a good charge confinement on the dots, because we must be sure that even with a temperature, we don't lose the information. Then, after we immobilize the molecule on a substrate, the geometry of the dots must be stable. Dots should not move around, because otherwise electrostatic interaction could and electrostatic properties could change. So the molecule must be fixed once it is on the substrate. The other clear important feature of the molecule is that it should allow for clocking, and that clocking means the molecule, the state of the molecule must be erasable when the clock is applied. So the first molecule that has been proposed in the literature is the one we see here. First proposed for other purposes by Aviram, and then studied by Lent and his co-workers a few years ago for this type of application. It is called a 2-allyl butane, based on 2 allyl groups here. Basically, it is based on, the 2 groups are based on methylene and on vinyl, the 2 allyl. And they are connected by 1 butyl group in the middle that works as a bridge between the 2 allyl. Every allyl has 2 occupied bonding and 1 non-bonding level. So one molecule can tunnel from one to the other end of the molecule. And this assures the 2-dot behavior. It has been analyzed and simulated using Gaussian, and simulation demonstrated that the homostates are well localized in the 2 allyl group. They can be in these 2 or delocalized in the 2 allyls, but in any case in the 2 ends, in the 2 extreme part of the molecules. So depending on the nearby molecules, the electron can go in one or the other zone. As a whole consideration, after the works proposed by Lent, basically this molecule shows a very high polarizability, provided that 1 unpaired electrons is present and can be mobile between the 2 allyl groups. And for the same reason, though, it shows good dipole moment. If a study is done forcing a charge, just a small charge, used as an input in order to mimic an input molecule. And so the dipole moment is a good one and demonstrates behavior like the one of a CMOS inverter. One input means 0 output. However, it does not show a possible null state and so clock cannot be used here. It's only a theoretical molecule, and moreover, it cannot be immobilized, at least in the present condition. The similar idea is at the basis of the 3-allyl case molecule, in which the allyl type is exactly the same, but this time 3 dots are available, almost identical, and so the fact that we have 3 dots allows to force a clock. And simulation demonstrated that, again, good homostructure are localized, well localized in the allyl, and also the electrostatic distribution shows these good properties. Again, this is a molecule that cannot be immobilized and still has not been synthesized, and has, from a practical point of view, many issues. The other molecule that has been proposed is the one I mentioned before, based on iron and ruthenium. In this case, there is not asymmetry between the 2 dots, because they are based on iron and ruthenium, and if the charge is localized in one of the 2 parts, then we have a 0 and a 1, or a 1. Here we see how the real molecule is, very complex, where we have a ferrocene basically here and a ruthenium structure here. But the property of this molecule is that it is realistic, it has been really synthesized, and also it has a part here that can be used to immobilize the molecule to a substrate. By means of simulation, we see that HOMO are well distributed, well localized in the 2 parts, even though it is clear that they are not equal. So it means that there is an asymmetry between the 2 parts, and also this from the computational point of view, the delay point of view in switching, and how the molecules can influence one another could give some issues. In any case, it has been used for demonstration, so a film of molecules have been fixed and immobilized over a silicon substrate in a vertical position. As I said before, a cap of mercury above has been connected to the ferrocene here, and a capacitance has been measured as we have seen before. So depending on the voltage, the positive or negative voltage applied between the 2 electrodes here, the charge was either negative or were clearly different, and so the charge variation between the states were clearly different between the 2 situations. Still, this molecule, even though it gave this good result, it has been abandoned, not used to study the properties and the feasibility, but still has not given a demonstration, a clear demonstration of the fact that one molecule can influence the other if we put them nearby. They just, as a film, give a good charge transfer behavior. Another molecule proposed for this structure is based on 4 dots of ferrocenes. And here we see the structure, and this is the ballistic structure, more easy to be analyzed. So we have 4 ferrocenes here around, and 1 cobalt structure in the middle to work as a bridge between the 4 dots. And here we see a section view. Basically, this is just a connection block, but hopefully it could work as a basic block to hold the null state. This molecule, studied by co-workers, again, of Lent, demonstrate a good bistable behavior in the diagonal. And also, the influence from one molecule to the other has been analyzed. So, which is the interaction? and using another molecule, one molecule as a driver and one molecule as a receiver, and changing the charge in the driver, then the charge of the receiver has been analyzed. And so we see that we have a good property here, because with negative charge value we have also well-defined negative charge V localization for the driver, for the receiver, sorry, and the same in the other side when the applied charge is positive. The two curves here are represent two behavior with different temperature. Clearly, at 0 Kelvin, the behavior is ideal, but in any case, we have a good behavior also if we are working at room temperature. Still, that molecule has been studied only in theory. More recently, an interesting molecule based on 3-ethylene group has been was proposed by Lent. It is called a decatrine and is based on carbon-carbon bonds, all similar. It represents just a 3 dots molecule, and it showed a good separation between the states and also shows a possible null state. Basically, the two extreme are the 2, 0, and 1 points, and the one in the middle is the null state. Still, it is theoretical in the sense that it cannot be stabilized on a substrate, at least in this as it is, and in any case, some problems from the synthesis point of view have been noted. A new molecule that has been proposed in literature very recently, and it has also been engineered and synthesized in reality, is called a bispherosine. Here we have the real formulation. And we basically have two ferrocins block separated by a carbazole block in the middle. This allows for 2 dots for the 0 and 1 state and 1 part for the null state. This molecule is a realistic one and can be stabilized on a substrate. In fact, it comes also with a thiol block here that can be connected to a substrate. This has been done on a gold substrate, for example, and this is an STM view of the molecule, and at least even without any field applied, we can see the 2 blocks with a third here in the middle that shows a good structure here, very also regularly organized with respect to the lattice in the substrate here, and it seems to be a very promising molecule. For what concerns the simulation, it has been analyzed also by in our university, and using 2 different clock fields. One clock field applied vertically to emulate the clock, and another horizontally to force the switch between one state and the other, 0, 1, and vice versa. So, how to simulate it? Because clearly we need, in this case, not only to analyze ab initio behavior, but also dynamic behavior. We need to simulate different fields, horizontal and vertical, and also fields that should be organized spatially in different zones. So simulation run were based both on Gaussian and on Material Studio, which allows for 2 electric fields in 2 directions. Still, both these 2 simulators only allow the static electric field, but in any case, it's a good starting point. So, without any electric field applied, the simulation pointed out the localized HOMO, partially localized in the carbazole. And this seems a good point for what concerns the null state. On the contrary, if an electric field is applied in the switch direction, here we see a top view of the molecule, then we see that the HOMO are well localized in the two ferrocins, showing that a good localization of charges is reached, and so it can encode very well 0 and 1s. Another interesting information can be reached if the charge is analyzed. In this sketch, we see all the dots, all the atoms in the molecule, and the color represents the charge associated to each atom when we have a switch electric field. In this case, we don't have any clock applied, so no clock in this direction, but just a switching field in this direction. In this case, we see that we have a good localization of charges. Still, we have a partial dipole internally inside the ferrocin, but in any case, as a whole, the two dots show a good charge localization. And if we move the clock from one direction to the opposite direction, we see that we have a good localization and motion of the charges. The other point is this. Up to now, we have seen just qualitative values. Okay, the charge is well distributed, but how big is that charge? Because we said that we need a good localization and stability of the charge localization. So as this is a totally new molecule that also must be analyzed not only from a static but from a dynamic point of view, the point is which basis set to be used to analyze it, to optimize it, to better represent and model it, which type of charge to analyze, the Mulliken, the Hirschfeld, the ESP charge modeling. So we in our university tried many simulations on this point and compared the two simulators. Clearly, it is not easy to make the correct choice. So one goes down to the to a drop of water first to see which is the best way to analyze things. Even though clearly the other molecule, the bisferrocin molecule, is much more complicated. So from the analysis of the water, we see basically here the charge for the carbon, and for the oxygen, and for the two hydrogen atoms. And what we see is that the ESP charge analysis is much more stable and not dependent on the type of functionals used to approximate the behavior of electrons inside the molecule, and also does not depend on the basis set. On the contrary, using the same simulator, which is Gaussian, the Mulliken charge shows a variation depending on the type of other approximation used. So ESP seems much more reliable. A similar result has been found also using the other simulator, which is Material Studio, which in any case shows a better stability for the ESP, even though a higher sensitivity is reached here. Similar comparison is done here for the bisferrocin. So here we have the charge distribution for all the molecules in all the atoms in the molecules, starting from carbon to iron, again carbon. They are just in a random order here. So here we see the charge of the iron here and here. And the different colors are for the different type of charges. So we see a pretty big variations depending on the type of analysis. And the same is present if we change the clock applied, so the vertical clock applied. In this case, we have no clocks. Here we have a positive clock in the vertical direction, so something is changing, but not too much. On the contrary, if we have a negative clock, then we have a very huge variation for the ESP charge. On the contrary, the Hirschfeld charge analysis is very similar to the previous one, and molecule is in the middle. So the charge analysis that seems in the same time stable and also gives more information is the ESP, that is the one chosen for this type of analysis. Another interesting information then is no more to analyze the charge on the single atoms, but to group using functional blocks in the molecule the charge. And so here we have, without any clock applied, the charge analysis of the blocks like the ferrocene, the two ferrocines, so the red and the green are the charge, just summing up all the charges in the atoms of the two ferrocines. Then the blue is for the carbazole, and the other are for the other blocks inside the molecule that are less important. What we see is that even though in this case we have a zero clock, if we change the electric field, positive or negative, in the horizontal direction, we see that the other blocks basically are not influenced. The charge remains stable. On the contrary, the charge of the two ferrocene group are very well influenced and also oppositely influenced. And the charge difference is around 2.5 units. Clearly, the electric field we force here is not small, around 5 or 10 electron volts per nanometers. If we change the clock from 0 to a negative or a positive state, what we see is that there still remains a good charge distinction between the two ferrocenes, while the other remains unchanged. But the total charge in the two ferrocenes, in the two dots, becomes negative. And so the positive charge is transferred on the thiol. If we change the clock from -10 to +10, we see a similar behavior, but in the opposite sign. So this is good enough to show not only a good stability of the two ferrocene blocks as dots, but also the fact that if we use the clock, we can transform the total charge as positive or negative, and this is promising for what concerns the readability of the cells, for the readout structure function of the cells. If we compare the same behavior of the ferrocene molecule with one of the previous that we analyzed, the decatrine, that one is the more recently proposed in literature, we see a similar behavior for the two dots, external dots, but the charge difference is much smaller, and this demonstrates how the bisferrocene is clearly a better choice with respect to this one, at least from the practical point of view, because the charge difference is much clearer, and so it is clearly more easy to be used from the experimental point of view. To conclude, here also we have a simulation demonstrated the dipole moment of the bisferrocene molecule, and clearly the X and Z dipole remains unchanged. On the contrary, the Y dipole is changed more or less linearly, changing the electric field applied, and so the total absolute value dipole moment shows a good stability of the molecule. To conclude, several open issues remains on not only these molecules, but on the whole QCA feasibility demonstration. One point is to analyze the influence between nearby molecules, which is the optimal distance, which is the realistic distance if we think at doing a film of molecule, and how these change if we mobilize the molecule on a gold or silicon substrate. Then also we must emulate, it is necessary to emulate an input. So one ongoing work is to put not exactly just one charge as done previously in literature or one electric field, but put a realistic molecule, and so the charge distribution of one input molecule in order to see what happens to the molecule, to the driven molecule. And finally also it is important to be able to force clock in different field, in different part, and in a dynamic way in order to apply different clock zones. And clearly all this must be analyzed and must be proven by experiments. So these are all the ongoing work, and we hope to be able to demonstrate in a short time that QCA could be a good choice for the future.